Hi, it's John here. Welcome back to part 2 of, hopefully 2 parts, of a deep dive into the instruction set. In the previous video we managed to get up to the branching instructions, so I'm hoping that we will get and finish off the instruction set in this video. So let's get cracking. So the next instruction that we was going to look at was the compare. Now this allows you to compare the contents of the accumulator with the memory contents, and what happens is it compares the two and sets these 3 flags depending on the result of the compare. So if you compare 10 with 10, then the 0 flag will be set to say that they're the same. If you're comparing 10 with 11, then the 0 flag will be not set, so it's not equal to, and stuff like that. So what we're going to do is we're going to do that and see what end results we get out of the system. All right. So we'll load the accumulator with D2. And then we'll compare it with 9.2. We'll compare it with D2. We'll compare it with FF. So as you can see here, we're going to compare it with a number that's less than itself. We're going to compare it with a number that's itself, and compare it with a number that's bigger than itself. Alright, so we'll get rid of that, and we will see what we're going to get. So let's go into debug mode. So we'll run into the instruction. So here we go, we're going to load the accumulator with D2. Now we've compared it with D2 and compare it with 92, and as you can see, the carry flag's been set, and that's it. So it looks like the carry flag identifies if it's less than it. So we'll see if that's the case. So we'll execute the next one, which was compare it with D2, and as you can see, the 0 flag is set, so it's equal to, and the carry flag is set, so it's equal to and less than. I think that's just a carryover. So what we need to do is we need to clear these flags out when we're running it. So let's do that. So loading. So let's clear out all the flags. So clear out V, clear out C, clear. Oh, we can't clear the 0 flag. So we'll do that on every one of the compares. So clear it out there, clear it out there, and clear it out there. There we go. So we'll run into it again. So we're going to clear out the flags. Yeah. So we've got nothing set. Load the accumulator, and the negative flag is set. I don't think we can clear that out. No, we don't. So we'll clear out the flags and then we'll compare it. So the branch if carry clear is the carry's flag's been set, which gives the impression that that's your test if less than. We'll clear them out again and then do D2. Oh, so it does set both of them, so it's equal to or less than. So we'll move to the next one, clear them out again, and we'll test with FF. So the negative flag's been set, so but these two have not. So the carry looks like if it's clear, it's greater than, and the negative one's been set because of the negative flag being set on. So there is some logic behind the compare and what happens to the flags. So sorry about that, had a phone call. So in summary then, after a compare with all these flags being set, we end up with that if the 0 flag is set to 0, it means that the accumulator is not equal to the number that's been presented, and so you can use a branch if not equal. If Z is equal to 1, that means that the accumulator was equal to the number, and therefore you can use a branch if equal. If the carry was 0, it means that the accumulator was bigger than the number was bigger than the accumulator, and therefore you can use a branch if carry clear. So, if it's greater than. And if the carry is set to 1, it means that the accumulator was less than or equal to the number, and therefore branch if carry set. Now these rules are global for the other compare types. For example, compare X, CPX and CPY have exactly the same effect as the CMP with the accumulator. So these rules will still apply even for those comparative types. Right? And I won't do the same with the CPX and CPY because they are exactly the same as the accumulator. It's just that instead of testing the accumulator, they're testing the X register or they're testing the Y register. The next one is to decrement a memory address, and basically it means you specify a memory address and it will decrement it by 1, and it will set these two registers. So if it becomes a negative value, that is flagged. If it becomes a 0, then that is flagged as well. So we'll just do a quick run on that. So we'll stop the debugger while we do it. So get rid of all this and we'll decrement what memory item. We will decrement 0830. That should be outside of our scope. Right, so we'll save that and debug it. So we're going to jump into the debugger, and I'm going to get the memory location set up. So 0830. So there it's 55, look. Okay, it's 55. So if we run into it, so we're going to jump into it. Here we go. We're going to decrement it now. So straight away it's gone to 54 and none of the flags have tested. So that is what decrement does. It just decreases the memory location content by 1. Hence that. We've got the same with DEX and DEY, but the only difference here is we're decrementing the index X by 1 and then putting it back in the index, and decrementing the Y index by 1 and putting it back in the Y index, and we still can test the statuses after that. So the next instruction is exclusiveor, and an exclusiveor is like an OR but with a special criteria, and these two status register points will be set as a result of that. Now an exclusiveor, its truth table is something like this. So if both the digits are the same, then it's not set. If they are different, then it is set. So 1 and 1 exclusiveor 1 is equal to 0. 1 and 0 and exclusiveor 0 is equal to 1. 0 exclusiveor 1 is 1, and 0 exclusive 0 is 0. So in this case, so we got 1 and so the different is 1, the same it becomes 0, different it's 1, different is 1, same is 0, different is 1, different is 1, same is 0. So if we put that into the code and see what the end result is, we should end up with this at the bottom. So we should end up with 101101110. Well, in that case is B6. So let's load it up. So we'll load the accumulator up with the binary number 10010011. Oops, wrong one. 1001011, and then we'll exclusive OR it with the other one below it, which is 1001 001 001 101 001 001 001 101. I think that's what it said. 001 00101. Yeah. So we'll run this through the debugger, and we'll see what it does. So there we go. So we load 93, exclusive OR it with 25, gives us B6. Yeah, there we go. And that is a very good instruction to learn, because it's great to be able to turn non-matching bits on and matching bits off in one instruction. Okay, so we move on to the next instruction, which is increment memory location. So we'll do the same thing as we did before, is we'll just, instead of decrementing, we'll increment the location. So I think it was 0830, so we'll inc the memory location 0830. So we'll send that to the debugger and we'll watch what happens. So there we go, 0830 is set to 55, and we'll step into it, increase, and it changes to 56. And it's as simple as that. So it's a quick way of adding one to a memory location, just as the other decrement instruction was a quick way of decreasing by one. And you have the same with the registers as well, so you can increase X by 1 and increase Y by 1, which is the reverse of the decrement, and they are only affecting their own register memory space. Jump, well, a jump to a new location is that we're jumping to a new location, and we've been doing that from the start, because if you notice on this I actually do a jump to start. So when we go into the debug program, the very first instruction is jump start, which is 0804, which is actually here, 0804. And it's just a quick way of getting from one area of the memory to the other. Yeah. Jump with subroutine. This allows you to jump to like a jump goes to another part of the memory to run a routine, and then returns back once you've finished and call and execute the RTS, return from subroutine command. And what it does, it puts where you've come from. So if you jump from 0800 to 0900, it puts on the stack the program counter 0800 onto the stack, and then when you come to do an RTS, it brings back the 2 memory bytes, the program counter, off the stack, and sets that as its new program counter, which then effectively sends it back to where it came from. And so it's very useful for doing subroutines. Loadx, well, this is exactly the same as load accumulator. The only difference is we're loading into the X registry, and has the same effects on the statuses as the load accumulator. We also have load Y, so you can load into the Y registry directly, and has the same effect as the other loads. So here we go. We had logical shift left. We've now got the reverse, which is logical shift right, where it shuffles all the bits to the right and the bit that falls out goes into the accumulator. So it does the opposite of shifting left, with what I've shown you before. It shifts right. We'll do that. So we'll use the LDA here, and we're going to shift right, so logically shift right the accumulator, and we should end up with it looking like this. So 01, 001, 001, and then a 1 C is equal to 1 because it drops this C off. Alright, so if I do a quick workout, 01, 001, 001 should give us an accumulator value of 49. So let's send this to the debug program and we'll jump into it. So you get load 93, logically shift it right, we get 1 in the accumulator and we get 49. So that's shuffled it across and added the 0 to the end into the leading bit. The next instruction is an OR. Now the OR is very similar to an exclusive OR but doesn't have the special instruction. So an OR truth table would be if both are if both of them are 1, then it results in a 1, or if there's any 1 in any of the inputs will result as a 1. So it'd be 1 or 1 equals 1, 1 or 0 equals 1, 0 or 1 equals 1, and 0 or 0 equals 0. So when you do this truth table here, so it's 1 and 0 is 1, 0, 0 is 0, that's going to be 1, that's going to be 1, that's going to be 0, that's going to be 1, 1, and that's a 1. There we go. So we'll put that into the program. So we'll load, I think it's the same number, isn't it? 1001011. Yeah. And then instead of exclusively ORing, we're going to OR it. So we'll copy that and paste it in there. So ORA, and that's the number that we're ORing. 001000101. Yeah. We're not going to increment it, and we should end up with the value is 1011011 is B7, I think. B7. So we'll run it and see if we get B7. So here we go. So we jump into it, load 93, OR it with 25, and we get an accumulator of B7. Hey, love it when a plan comes together. And so that is just a simple way of ORing two bits together to combine them. So if any one is set, it will always be set. Now, the stack can be interfaced with, but it can only be interfaced with certain things. So you can only push the accumulator to the stack and the process register onto the stack. Alright, so when you want to temporarily slow the X and Y, you have to push the accumulator to the stack, then transfer X into A, push that, transfer Y into A, push that, and I can show you that in some code in this demo I've got here, because I do that on the print. So if I look at the print accumulator, first thing I do is I push the accumulator onto the stack, transfer X into A, push that onto the stack, transfer Y into A, and push that onto the stack. And then the reverse, to bring it back, you pull from the stack, transfer A into Y, pull from the stack, A to X, pull from the stack for the accumulator. You can push the process status to the stack, as well as pull it, and I think that's the next one here. Yeah, so there we're going to pull from the stack and pull the status register from the stack. Then, as we've done logically shift left and logically shift right, we can do rotate left and rotate right. And what that allows us to do is we can set the carry flag and spit that in the bit that's moving away, and then the bit that's falling off the end can get put into the carry, and we can sort of rotate round the system, and we can demonstrate that pretty easily. And rotate right is just the same. So we'll do both of these instructions here. So what I'm going to do I'm going to set the accumulator to nothing. Yeah, but I'm going to set the carry, and then I'm going to do rotate right, and we're going to do that 4 times turns. So we're going to rotate right. So we're going to stick it into the top significant bit and watch it move down, and watch this one move down. Yeah, and then on the flip side, we're going to rotate left, and we'll do the same number. So what should happen is that the carry will get sent in, and we're going to rotate it down, so the number will get smaller and smaller and smaller, and then when we come to rolling it back up, the number should get bigger and bigger and bigger until it comes back to 0, and then the carry is set. So we'll show that in here. So we're going to jump into it. So loading the accumulator with nothing. The carry is clear, as you can see. So we're going to set the carry to 1, and then we're going to roll it in. So straight away it becomes 80. We're going to rotate it again, should become 40. Then it rotate again, 20. Then rotate it again, it's 10. But now we're coming to the rotate left, so we're going to start shuffling it back up. So it should be, when we do a rotate left, should become 20. Then it comes 40. Then it becomes 80, so you can imagine that bit moving along, and then it comes out back into the carry. And we could have carried on doing that, and it would have rotated that bit all the way round until we decided that enough was enough. There is no start or end, it's just rotating round. It's not like the other one where it rotates one way, but it only puts a 0 in, it only injects a 0 and drops out into the carry. This is actually injecting the carry and dropping out the carry, so you could forever just rotate it round forever and a day. Return from interrupt. This is where if you hijack the interrupt, and I've done this on another video when I've been talking about my my disk operating system. When you hijack the interrupt, you've got to return to the interrupt in your code. You can't do an RTS because the system will just fall over and run out of stack. So you have to do an RTI, which means return to interrupt. And so it pulls the status register and the PC counter from the stack, and then returns you back to where the interrupt had started off and the state of that interrupt. Return from subroutine, well, we've talked about that when we did the jump go sub. So that just returns you back to the place where you started plus 1 program counter. Subtract is exactly the same as add, but in reverse. So what it does, it takes the accumulator, then you minus your memory, and then you minus the carry. So if the carry is set to 1, it will minus 1 as well. And so it's exactly the same as the add, and we can demonstrate that if you want. So we'll say that the accumulator is 83, we'll clear the carry, and we'll add with carry 2. Then we'll set the carry. It's not add, it's subtract, isn't it? And then we'll set the carry and then subtract another 2. So if we're going to debug, so we'll jump into it, load 83, we're clearing the carry, then we're going to subtract 2, which should bring it back to 81. But no, it subtracted 2 because the carry was clear. So it actually subtracts 3. So this time we're going to set the carry and we're going to subtract 2. So this should be 7E. There you go. And because the carry was set, it only subtracts the number that you've specified. If the carry is clear, it deletes 1 more because the carry was cleared from the previous subtract or add. Alright. The next instruction is set carry and set the decimal flag. Well, we've seen the clear ones, so these are the set ones. and you can set the interrupt. That's disabling the interrupt. Now store the accumulator is exactly the same as load, but you're storing it, you're taking the contents of the accumulator and storing it in memory, and we've seen this being done in previous tutorials. And you have the same instruction for store X and store Y. So it's storing the contents of X and put it in memory, storing the contents of Y and putting it in memory. We've got transfer accumulator to index X, which basically transfers the number out of the accumulator and puts it into index X. And same with transfer A into Y, transfers the accumulator into Y. And then we've also got transfer the stack pointer into X, and that's the stack pointer of the stack, and transfer the X value, the contents of X, into the accumulator. We have transfer X into the stack pointer, so you can move that about, and then transfer the contents of Y into the accumulator. And I think that's all the instructions in the 6502. Oh, and that's half an hour. Right, so I hope this has been an informative set of videos, and in the next tutorial we'll get down to some nitty-gritty and make some little programs that sort of stitch everything together. Okay, well, thank you very much for watching, and I'll see you in the next video.